So then I'm calling the next speaker actually. So that's Alex, University of Barcelona. Again, the group we've been working with since quite some time, and he's talking about work they've been monitoring for quite some time, and we started to act actually. I'll get back to it later. Maybe Alex is going to talk about that. So he's going to talk about the use of selective plastic scintillation microspheres. So using a solid scintillator and adding selectivity to that. So with that, thank you very much for being here, to presenting, and the floor is yours.
Thank you, Stephen, for your presentation. So good afternoon to everybody. I will share my, let's see. Okay. If now, I think you can see my screen.
Yeah, that's perfect.
Yes. Yeah, you can see my screen. Okay. 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 So good afternoon to everybody. So thank you very much. So for giving me the opportunity to give this presentation about our work with plastic scintillator and this view on how to achieve selectivity measurements of radioactivity with plastic scintillators. So why we choose plastic scintillators? So plastic scintillators has come historically in parallel with liquid scintillators, but in the last 20 years we have observed a quite increase in its use. Things basically because the development of new materials, new plastic scintillator, new polymers, and also some new applications and neutron gamma discrimination. So there is recently a book talking about that in the progress done in the plastic scintillators in the last years, and why plastic scintillators are a good option for radioactivity detection. So the main characteristic is their versatility. So you can find polymers of different compositions, different base polymers with different properties. You can prepare polymers, plastic scintillators in different shapes and sizes, from microspheres to blocks or fibers. And also you can add several additives that changes the properties of the plastic scintillators. Sorry. In the case of selectivity, you can have the possibility to cause modifications on the surface of the plastic scintillator and even on the internal part of the plastic scintillator. So these options are, for example, the position of a structure in the surface of the plastic scintillator. This one option. The other option is to link the extraction to the surface of the plastic scintillator, and finally to add, to imprint the surface or the inner part of the plastic scintillator with cavities that are selective to the analyte you want to analyze. In this case, the radionuclide. So we have mainly worked in the deposition of the extraction on the surface of the scintillator, although we are also working in these two possibilities because they offer new capabilities of capacity and resistivity of the extraction of the separation. In our case, we have worked with with plastic microspheres, plastic scintillators in form of microspheres, but also in kits. I will present very shortly our recent work in plastic scintillation kits and also in foils. So essentially in the use of plastic scintillation resins, the plastic scintillation resin is a microsphere of polystyrene with fluorescent solutes coated with a selective extractant. So the idea is that you can put this resin into a solid phase extraction cartridge as the one that typically is used for chemical separations, and then proceed with the chemical separation in a vacuum box, for example, with advantage that at the end of the separation with the radionuclide retain, you can put the column into a 20 milliliter polyethylene vial and measured in the liquid scintillation detector. So if you have a sample with a mixture of radionuclides, the radionuclide of interest become retained in the cartridge with the plastic scintillation resin, the interference are eluted, and then you can measure directly, joining the measurement and the detection with the same vial. These present some advantages regarding traditional methods, because you can reduce the step of elution. So this is the typical scheme of separation with measurement by liquid scintillation or even alpha spectrometry. So you can avoid the elution step because you measure directly the radionuclide of interest retained in the column. This implies a reduction in the reagent uses and also a reduction on the time, because you skip the elution and the preparation of the liquid scintillation vial or the alpha spectrometry source. So going into detail on the plastic scintillator resins we have developed, we have worked on, and the different applications. So the first one, or let's say perhaps the main one, is the plastic scintillator resin based on a liquid 336, as we have seen in the past presentation from Nora. This equivalent to the TIBA resin with the quaternarium ammonium as an extractant. So here you have an image of the cartridge with 1 gram of the plastic scintillation resin. These cartridges are now commercialized by Trischem and are mainly thought for the analysis of technetium 99, as I will show you next. But it is also possible to make analysis of polonium 210 and also plutonium isotopes, and also some anionic species, as for example carbon thiocyanate as well. So for the case of technetium 99, this is the typical separation scheme with a conditioning of the plastic scintillation resin with a chlorhydric acid 0.1 molar, loading of the sample in the same medium, 10 milliliters or higher, because it has a high breakthrough volume, and then cleaning with just water, or even cleaning with nitric acid and fluoridic acid if uranium is maybe present in the sample. For this separation, we use rhenium as a tracer of the separation, as there is no stable element of technetium. These are the values of yield and detection efficiency. So we have quantitative yield, we have very high detection efficiency with a spectra quite located at high energies, and also we have a low background. This is quite relevant. In this case, we have a low background because we are just using 1 gram of plastic scintillator. So comparing with the 20 milliliters of a liquid scintillation vial, we can achieve a quite low background in the measurement in this case in a quantum loss detector. We have also evaluated the breakthrough volume, which is higher than 200 milliliters, and even we have done some tests with half a liter working perfectly. So very high breakthrough volume. And these are two examples of sample analysis, in this case, spigot samples of seawater and urine. In this case, in the case of seawater, the sample was analyzed directly with quite low errors, and in the case of urine, there is the need to make a pretreatment in order to avoid the presence of organic material in the sample. So you have to treat with nitric acid and also evaporate to dryness and heat in the muffle oven to remove the organic matter. So here you have the data for both samples. In this case, 100 milliliter of urine or 100 milliliter of water. So 100% recovery, very low background, and detection limit around 0.024 becquerels liter, which is quite low for a 24-hour measurement. So this is the main application, the analysis of technetium 99. But there is also other possibilities, and we have been working in this last year in two applications. One of them is plutonium, as we have seen in the past presentation. The liquid 336 thickest thin resin has a very good retention of plutonium in nitric 3 molar acid, and this is the basis of the scheme separation to retain only plutonium in the resin. So as the plutonium has to be in plutonium 4, first is need to do the balance adjustment to plutonium 4, and then the sample is loaded in a medium including nitric acid, aluminum nitrate, and also chlorhydric acid. The column is rinsed first with nitric acid, then with chlorhydric 9 molar, in this case to remove thorium that can become retained, and finally to remove neptunium 0.5 molar nitric acid. So in this case, to trace the separation, we use gold. We study different tracers, and we found that gold can be used as tracer, but in this case, it is necessary to add chlorhydric acid to the media in order to stabilize gold. So this is why we add also chlorhydric acid in the loading medium. So here there is the spectra we obtain in the separation of plutonium with gold as tracer. The spectra is quite broad, and this is because there is a slightly yellow color caused by gold in the retection. Nevertheless, we have a very good yield, almost quantitative, and very good detection efficiency, which makes possible the quantification of plutonium. So here is one example of analysis of a water sample. We just evaporate to dryness, and then we treat the residue with nitric acid and chlorhydric acid. And after dryness again, we reconstruct, and then we follow with the chemical separation, balance adjustment, and separation through the column. So results obtained at quite satisfactory, with errors lower than 10%, and with a low detection limit of detection, taking into account that we are measuring in this case a 100 milliliter sample, so we can increase the volume, and also the time, because we were more focusing this study in the possible measurement of plutonium in an emergency, so obtaining a fast methodology. The second new application is the analysis of polonium, because again, it is described that in a chlorhydric acid specifically, there is a very good retention of polonium in the resin. So the first we studied was the elution of lead and bismuth, as it can be interference in this determination, and we determined that with chlorhydric acid, sample loading, but also with the first cleaning, and using chlorhydric acid 6.25 molar, we can remove strip lead to 10 and bismuth to 10 from the column. So we applied this procedure for the separation, using in this case cadmium as tracer, because it has a very similar behavior to polonium in this situation, loading with chlorhydric acid 1 molar, and cleaning with chlorhydric acid 1 molar and chlorhydric acid 6.25 molar. We have quantitative retention and a spectra, in this case, very, very sharp and located at high energies with 100% of efficiency for plutonium 220. So this is the complete scheme of separation, of analysis of a water sample, in this case 0.5 liters. So we add the tracer cadmium, then we precipitate with manganese, we filter in basic medium, we filtrate the precipitate and redissolve it with chlorhydric acid with peroxide hydrogen, and then we digest the sample in order to have the polonium in 4 excitation state. And finally, we pass the sample through the column in this chlorhydric acid medium. The column is measured directly in the liquid scintillator, and the different liquids of the treatment are measured by ECPS, OS, and MS to determine the cadmium recovery. We have compared the analysis of polonium with the plastic scintillator resin compared to 2 methods based on alpha spectrometry, and what we found is that we have a quite high detection efficiency. As you can see here, a high detection efficiency we compare with alpha spectrometry. Also high background, because this is scintillation, but the limit of detection are comparable. So we have quite a similar limit of detection in this case for 69 hours of counting. We analyze a reference material with the three methods, and we obtain comparable results in terms of relative error and relative standard deviation, with lower time of analysis, thanks to the fact that we do not require for alpha spectrometry preparation sources. So we have improvement on the time of analysis. So these are the results obtained for the TK-TC scintillation resin. Another resin in which we have been working during several years, and we are doing more procedures of analysis, is the one based on a chrome ether. This is the typical chrome ether used for the analysis of strontium and lead also. Here are the data for the separation of strontium-19 or strontium-89. So you can condition the column with a nitric acid. Then the sample has to be passed on nitric acid, 6 molar or 8 molar. And then important in this case, during the cleaning procedure, you have to use, as a last step, lithium nitrate to avoid chemiluminescence caused by the presence of high concentration of acid in the column. As tracer, we use a stable strontium, 1 to 5 milligrams. In the case of 5 milligrams, we usually use a higher quantity of resin in the cartridge. Here are the data, the spectra for strontium-89 and strontium-90, and the spectra, and the data of efficiency, so high efficiency. And we have done some applications. I will show you two. The analysis of milk. This is done in collaboration with the University of Politécnica of Valencia. And in this case, the sample treatment with a sample of 100 milliliters of milk is use of trichloroacetic acid to remove fat and proteins, and then precipitations with oxalates, and then the pass of the sample dissolved in nitric acid 6 molar through the cartridge. This whole procedure can be done in 5 hours, including 1 hour for a measurement, so it's a very fast method. Recoveries are quite high, the pretreatment and the column separations, and more important, even very, very reproducible. And quantification of strontium-19 and strontium-89 together, radiostrontium, was quite nice. Here are the data also for a reference material, a milk powder. And in this case, taking into account that strontium-89 was decayed, if we measure only taking into account the efficiency for strontium-90, we have very, very good results of activity determination. The same procedure was applied for filters and vegetation. In this case, we add ashing and microwave digestion to achieve a complete dissolution of the sample. And again, we have good recoveries for the whole procedure and good determinations even at different activities proportions of strontium-89 and strontium-90. Regarding analysis of strontium-90, we are working now in 3 topics. The first one is the analysis of strontium in environmental samples, taking into account that the samples can contain lead-210, which can be an interference that is also retained in the column. And for that reason, we add a separation step in which we precipitate lead in form of lead iodate using a hot nitric 8 molar solution in which lead becomes precipitated. So here are the results obtained for a sample including several interferences. This is an interlaboratory sample in which we have almost complete removal of lead, and here also we have the possibility to measure in a counting window in which lead-210 is not included, because lead-210 appears at very low energies. So we have very, very good low background, in this case for strontium-90. And quantification just after separation and after yttrium in growth are quite comparable to the reference value. Second application we are working on in collaboration with the University Rovira i Virgili in Tarragona is the measurement of all 3 isotopes in sediments. And in this case, polonium will be analyzed by alpha spectrometry, and strontium and lead-210 will be analyzed on by after its retention in the plastic scintillation resin. And a third, which is in the initial steps, is the analysis of strontium 90 in concrete decommissioning samples. So this is the second resin I want to present, and the third one and last is the one that we are developing the last year, which is a resin based on diphenyl metandiphosphonic acid. This is the base group for the retention of the actinides, the metandiphosphonic acid, with a silicium radical attached. So this extraction on the plastic scintillation achieves very good efficiencies for almost quantitative, almost 100% for all the alpha emitters and the actinides, and also quantitative retention in chlorhydric 0.5 molar medium, which is the first volume media we evaluate. We have very high breakthrough volume, higher than 400 milliliters, and we have considered the use of europium as tracer. So we have enough capacity, because europium is not expected to be in the sample, to trace the procedure of separation of actinides. So this resin could be ready for analysis of the whole actinides on the sample. We have studied the retention of different elements commonly found in samples in different media in order to define conditions in which we can increase the possibilities of use of this resin. What we have found is that at very low acid concentrations, it is possible to do a gross alpha analysis that includes also polonium and radium, and we are working on alpha beta discrimination on that to achieve the gross alpha parameter using this resin, but also individual elements, as for example yttrium-90 of uranium. We are evaluating different elution media to achieve this objective. So this is work in progress. And last, I want to present is the plastic scintillation kits. I say just 2 slides showing the idea. The idea is to make a kind of ultra-fast pseudo-quantitative here. Or important idea is to not to make a quantitative but pseudo-quantitative selective measurement in case of specifically decommissioning, but also it could be of interest in environmental and medical isotope cases. The idea here is to determine very fast if one liquid sample contains or not a radionuclide of interest. So the idea is you have directly the plastic scintillator prepared with the plastic scintillator disc on the bottom and the extraction on the surface of the plastic scintillation disc. This is already prepared. Then you have the sample with a mix of radionuclides. You mix with the kit, you shake it, and then the radionuclide of interest is retained on the extraction. Remove the solution, and you have the plastic the vial with the extraction directly. Attach it to the scintillator and measure it on the scintillator counter. So the idea is that you can perform all these analyses, all these steps, just in 10 minutes. So a very quite fast analysis with a pseudo-quantitative objective. So we have developed in vials, in glass vials, but also in plastic vials, in this case using the extractant for technetium 99, because we have several experience on that and it works very well. And here I just show you the performance after the study of the contact time of the solution with the vial. And here the most relevant perhaps is in 10 minutes we can achieve a 62% of retention. So we are capable to attach with efficiency the radionuclide on the kit and also detect it very well. So it allows this semi-quantitative ultra-fast determination. So this is the different developments I want to show you. So future work, so we are plenty of ideas to work on the future. So new plastic scintillators to improve separation in columns with porous scintillators with more capacity. Of course, more applications of the technetium scintillator resin for polonium in norm lixiviates or plutonium in filters and vegetation, the gross alpha in the Dipix-based resin. Also to make a proof of concept of the plastic scintillation kits, test more extractants, and important also to test samples, more real samples, to see if we can make this selective determination. To make analysis with two couplet plastic scintillation resins, and also new resins, for example, one for lead-210, based on a new extraction in collaboration with Trischem, imprinted scintillating polymers, and covalent bonding plastic scintillation resin. So we have been working on that on nickel 63, and we are having now quite promising results. So I want to acknowledge to all financial bodies, the Spanish government, the Spanish Nuclear Security Council, and the government of the regional government of Catalonia, and also the university for Predox grants. So thank you very much for your attention.
Yeah. Oh, thank you very much, Alex, for the very interesting presentation. Very nice overview over the possibilities of impregnated plastic scintillation microspheres. And yeah, as I said, something that we follow some time with interest. I mean, we're working together already. And I think there's indeed a couple of very, very nice applications out there, not only environment, also in decommissioning, rapid results. I think QC of medical radionuclides. There's some good applications. So I'm sure we will continue cooperating on that. So thank you very much. Okay, I have already two questions. So one from Nora. So she's wondering about the internal standards that you're using. So using the gold for plutonium and cadmium for polonium. So why you choose them and how you can be sure that they fit in terms of chemistry.
Okay. Yes. So in this case, we have selected. I have only shown gold and cadmium because they are the ones that present similar results to plutonium and polonium, respectively. So we have tested several. So we have make a search on the bibliography on the different media we have been we use. And we test several radionuclides, several methods. In the case of plutonium, we use samarium, europium, and tin, also several, molybdenum. So what we found is that gold behaves very similar to plutonium. Also, when we have not 100% retention, the quantification is good. And because both behave in the same way, the fact that the spectra is moved to low energy, slightly moved to low energy, indicates that it's retained in the same position where the color is present. So this is good indicative. So after separation, we test sample treatment. So because the ideal is that both elements behave during the whole process. So for water, gold is behaving exactly in the same way like plutonium, and the same happens with cadmium. So it's an experimental approach, let's say.
Okay, thank you. Question from NASA. Okay, tritium.
Yes.
How is yeah, solid cantilever scintillation? How is it doing the PSM? How are they doing it with tritium in terms of detection limit?
Yeah. Here, tritium with such low energy, it depends a lot on the diameter of the microspheres. So if we have studied from few micrometers to hundreds of micrometers, so the highest value we have achieved is 4%. We can detect tritium, 4% of efficiency. If you are working with 60 micrometers, which are the typical ones that we use because are very easy to manipulate, we are dealing with 100% of efficiency. So we can detect tritium. Of course, limits of detection are higher because the low energy makes it difficult to measure.
Okay, thank you. And question on the PS kit. Do you have to mix it the whole time or let it stand? So when you contact your solution with the PS kit, do you shake it the whole 10 minutes or 6 minutes, or you just short mix and then let it stand?
This is something that we have evaluated. So we have several results on that. I have present only the idea in the first results. We have checked, for example, just slightly agitation like this during a few time, also robust agitation like this, and also using a vortex. And what we have found is that the retention is quite robust, and the behavior of the yield is more robust than we expect. So we first think an agitation like this, but we found that simply do like this permits to have a good extraction of technetium 99. So perhaps we are dealing with the best scenario, which is technetium in a liquid, which behaves it's a very good scenario. But in this moment, the results are good. Nevertheless, for us, it's not important to have very high recovery, but to have extraction, because then we can assume that technetium is present in the sample.
So to think the extraction itself is very fast. You just need to get the technetium to the disk. Yeah. That's very interesting, and I'll get back to you with some kind of test stick approach on this one. So okay, I like the idea. Okay,
thank you.
Are there any more questions on your sides? So if there are no more questions, again, thank you very much.